Hi. At this point, we have done the main two steps of our strategy into the direction of understanding quantum mechanics. We have used a different method to derive the Schrödinger equation, the stochastic derivation, and we have seen that we can connect this derivation method to our own methods already demonstrated. This is important because we not only have a new approach to quantum mechanics, mathematical approach to quantum mechanics, but we also profit from a number of constructs that are akin to the new derivation and that can be used to interpret and understand quantum mechanics. So we have now the stochastic derivation as one of our own derivations, and we may now understand the role played by ensemble and single systems in quantum mechanics. This is the intention of this new video. So let's go. This discussion about if quantum mechanics is related to ensemble or single system is very old indeed. We have that quantum mechanics may be related to ensemble or may be related to single system. The fact is that in the literature and the history of quantum mechanics, there was a clear assumption that quantum mechanics is always valid for single systems. What we will show here is that there is not a clear cut between these two situations, these two ways of seeing quantum phenomena, but in fact that there is a connection between ensemble and single systems approaches, at least in some special cases. So let us see. We began our derivations of the Schrödinger equation only assuming that Liouville equation is valid for at least the integrated version of the Liouville equation is valid for quantum phenomena. But Liouville equation is clearly related to ensembles. So we know that quantum mechanics, if we assume the derivations, must be always valid for ensembles. The fact is that we know that in some situations at least, quantum mechanics is also valid for the explanation of single systems too. And we now want to know how can we connect these two pictures of quantum mechanics, special cases and special examples. So let us see. We now are convinced that quantum mechanics is related to random behavior. So let us think about some physical system in which the entity, the related underlying entity, is performing a random movement. We have here four realizations of this random movement. Of course, we would in general assume that we have an infinite number of realizations. This four here is just an example. We may take, in this case, an ensemble average by choosing some instant of time t0, and for each system, equally prepared system, we make our measurement in the system at the same time, and average is done over these results that I assigned here in the picture. So this is how we do ensemble averages. But look that we may also make, at least in some cases that I will clarify in the following, uh, single system averages. We may do, in these cases, averages over time. In this case, we take one system, only one system, this one for instance, and we follow the system making measurements along the time. Sometimes this is possible, not always, I will show you that. But whenever it is possible, we can do that too, and these are times average. So you have for these realizations, we have an ensemble picture in which we make averages along a single instant of time, and we have time averages in which we use only one system and make averages along the timeline. What we want to stress here is that there is indeed a connection for random system. Now we can use the fact that we are treating with random systems. There is a connection between the ensemble picture of these averages and the time picture of these averages. Indeed, we know that what connects the two pictures is the ergodic principle. If the systems that we are considering are governed by some sort of ergodic uh, behavior, it is seamless to make ensemble averages and time averages. They will give exactly the same result. So if this is true, at least for the systems where it is true, the old discussion about if quantum mechanics is related to ensemble or single systems is indeed vain, because of course the two pictures are identical. But the fact is that, as I will show you in other videos, in the next videos, the following ones, this connection between ensemble and time averages is not always possible. It's possible only depending on the way in which you make the experimental setup. And when we confound these two pictures for cases in which only the ensemble picture is applicable, we get a lot of weirdness in the explanation. I will show you that this weirdness is indeed related to assuming a time structure of averages, a time picture of single systems in quantum mechanics, when it's only applicable to the ensemble picture. So this is what I would like to introduce. Now we now have an assumption that we have to prove later on, that is that quantum mechanics is related indeed to the ergodic principle. We have not proved that, we have just assumed that this is possible. We will prove that in the next video. There are videos to follow later on. And we now assume that if this is true, we can connect ensemble and single systems interpretations of quantum mechanics, at least taking some caution with related to the application of these two pictures. Okay, in the next video I will show you exactly that. I will take the example of the Schrödinger cat, which is an example that brings about a lot of weirdness in the interpretation of quantum mechanics, and I will show you that this weirdness comes from the fact that we are trying to force into the phenomenon, the Gedanken experiment, single system interpretation when only an ensemble interpretation is possible. Thanks for watching.